Hi guys, thanks for tuning in. We're currently discussing some general aspects of the spectrum of bounded linear operators, mostly on Banach spaces. We have defined at this point the various components of the spectrum. We have done one example, and this was the right shift. We have computed everything explicitly, and this was quite a task, but now what we've started to do is we have assembled some more general facts about the spectrum that will help us in future examples. The first general fact was to do with the resolvent set. It stated that it is an open subset of the underlying scalar field, and there was also a resolvent formula which can be useful in applications. Now the next actually better fact here is on the slide. So if we're working in a complex Banach space, that is to say the underlying scalar field is the field of complex numbers and you have a bounded linear operator on it, then its spectrum is always non-empty. Okay. The fact that you have to work here over complex vector spaces shouldn't come as a surprise. If you just think about finite dimensional problems, if you, for instance, look at this matrix here, so that's a matrix 2 by 2 with real entries. It corresponds to an operator which is, a rotation. So then this matrix, since you're in finite dimensions, the spectrum is just a point spectrum. There's nothing else besides the eigenvalues. But this matrix doesn't have any real eigenvalues, right? The only eigenvalues are plus and minus the imaginary unit, right? So, and that being said, that word up there, complex Banach space, is maybe not so surprising after all. All right, so now a word of warning, or how to say, a word of looking ahead. So this theorem, as well as another one that we will discuss later on, its proof will rely on certain facts from complex analysis. So the theory of functions with complex input and complex output variables. Now, complex analysis is not a prerequisite of functional analysis in the version that I'm teaching it right now. And that being said, so if you have not taken a module in complex analysis, you can just fast forward. You don't need to bother about the proofs. Just live with the statement and be aware of the statement. If you have, however, taken complex analysis, then you will now see first this one, a very nice application of ideas from complex analysis in a completely different context, namely functional analysis. There are different ways to prove this statement, but none is as quick and as clean as using complex analysis. All right. So let's get started. So to prove this, again, we do very much the same thing as in the last result when we were proving the openness of the resolvent set. There we used essentially the Neumann series. So I will do the same thing. So I'm going to start writing first formally, and then I will ask myself convergence questions. So I'll pull out the factor lambda there, which is scalar. Then I have lambda minus 1t minus 1, and now, okay, suppose I will just use the Neumann series for this inverse there, identity minus lambda minus 1t. Then the Neumann series tells me, well, perhaps I can expand this in this infinite series, lambda to the minus n. If you view this actually as a series in lambda, now, first connection to complex analysis, this would be a Laurent series because the powers there are lambda with a negative n, right? And n is a strictly positive integer. Anyways, so this little computation motivates the following definition. R, say, hat of t, I will just define as 1 over lambda, 1 plus a series from 1 to infinity, t to the n, lambda minus n. And now, of course, we want this to be convergent. So now the usual thing happens if I were to estimate this in operator norm. Then I would get an upper bound. Remember, the operator norm is submultiplicative. I would get this one divided by lambda to the power n, right? So in other words, t lambda raised to the power n. That would give you an upper bound for the operator norm of what goes on under the summation sign. And you want this to converge, so remembering the geometric series, remember this here on the right, these are just scalar entries. So perhaps this series is convergent as long as lambda is outside a disk of radius, which is the operator norm of t. Okay, enforcing this constraint there in blue, immediately you can estimate that series there, and you will be able to prove that it is indeed convergent. That's precisely how the lambda is chosen. All right, this series converges in the operator norm. The operator norm for lambda outside this disk. Again, in the language of complex analysis, what I'm doing right now is I'm setting up a Laurent series expansion of the resolvent at infinity, actually. All right, and its sum is indeed, well, this you prove again how we prove the Neumann series, how you prove in the theorem about openness of the resolvent set. You just take a limit and you multiply things together, and you will see that this sum, I will underline it in green in a moment, is just equal to this. Okay, this sum here is just equal to this. Okay, good. Thus, this is just a preparation. Thus, as lambda goes to infinity, we conclude that the resolvent in operator norm for any bounded linear operator, well, it goes to 0. Okay, as lambda goes to infinity in complex modulus. This is also written, right? And why is this? Well, because up here my formula has two parts. Okay, so this part here, the red one underlined, is just, you can estimate the way I did it in yellow, and you will get a finite number, scalar number. And then out front you got here this lone sum 1 over n, 1 over lambda. So when lambda becomes large in complex modulus, that will drag everything to 0. And that's why you have indeed this statement down there. Okay, this statement, again, it shouldn't come as a surprise, because sort of formally, it's not very rigorous, of course. You can write it like this. Of course, this equation doesn't make any sense. There's no 1 over quantity here in functional analysis, because these are all operators, right? But sort of if t were a scalar, you would write it like this. And then, of course, when lambda goes to infinity and that scalar is fixed, you would expect that this will go to 0. Okay, that's sort of the formal reason. Let's erase it quickly again. Okay, so here's the rigorous argument that I just spilled out. Now, this is going to be a proof by contradiction. So now let's assume the spectrum were empty. Sigma of t is the empty set, where empty. Yeah, well, that means that then the resolvent set is the full complex plane. Remember, this statement is about Banach spaces over the complex number field. All right. And then the resolvent set is the entire complex plane. And the previous, this was a, what was this, a proposition. The previous proposition shows that, so in the previous proposition we did a similar expansion for the resolvent. It took a center point, lambda naught, and then expanded the resolvent into a series that was actually convergent in a little disk around that center lambda naught, right? So, but now if we were to assume that the resolvent set is the whole complex plane, then this working in the last proposition shows that the following function, g of lambda, which is the resolvent lambda t acting on an element in your Banach space, and then the result you stick into f. So this would be now a mapping in lambda from rho of t going into the complex plane, is an analytic function in lambda in rho of t in C for any continuous linear functional on your Banach space and vector in it. all right? So what am I saying here? So now this builds heavily a bridge to complex analysis. So what are analytic functions? So complex analytic functions, not real analytic ones. So complex analytic functions are those that you can locally expand into Taylor series, and the Taylor series converges in the whole disk to your function. All right, so this is the lifting of what real analyticity does to the complex plane. All right. And now here, since our resolvent in the previous proposition was expanded in just such a power series, assuming that the resolvent set is the full complex plane immediately implies that this function here, g, which is a function that maps complex plane or resolvent set, but which is the complex plane by assumption, to the complex plane, is analytic everywhere. It's analytic everywhere, okay? Because the power series converges everywhere, right? You can do that local expansion at each point that you like in the whole complex plane without any obstacles, all right? Yeah, but that simply means then that this function g is what you call an entire function in complex analysis, all right? So hence, g of lambda is, or just g is the function, g of lambda is its value, is an entire function. That means it is analytic everywhere. And there's one big theorem about entire functions that one usually mentions in complex analysis. The entire functions that are bounded in the entire complex plane, those have to be constant. This is a remarkable fact. And that's precisely what we're facing here, right? Hence, g is an entire function, and using this guy up here, we have that g of lambda goes to 0 as lambda goes to infinity, right? So, and remember, analyticity means you can expand it everywhere into a convergent power series, and at infinity it is bounded, and that means that your entire function small g is bounded everywhere. Hence, by Liouville's theorem, it has to be constant. Okay, so this now uses heavily complex analysis. By Liouville's theorem, therefore, this function has to be constant, and of course the value of the constant, because at infinity it vanishes, it has to be 0. So g of lambda is identically 0. Okay, by Liouville's theorem, did I write this? Yeah, by Liouville's theorem, therefore, g is identically 0, which implies, well, that the resolvent here has to be identically 0. Okay, so that is the 0 operator. But this contradicts our expansion, contradicting this expansion up here, this one here, because here, maybe let's do yellow, no, yellow star is already taken, that's double yellow star. It contradicts this, right, because here to leading order, you got 1 over lambda times the identity, and then higher powers of 1 over lambda, right? So this cannot be identically 0, okay? Which contradicts this one, okay? Hence our assumption was false, that is that the spectrum is empty, and that completes the proof, okay? So this is, in my opinion, a beautiful application of complex analytical techniques to prove something in functional analysis. All right, but again, if you haven't taken that module, just skip over the proof. Maybe once you have taken the module, go back to it and realize what we were doing here. Just live with the result for the moment. All right, now corollary, let X be a Banach space. And TLX bounded linear operator. Then more properties about the spectrum. The spectrum as a subset of the scalar field is compact, right? And since here our scalar field is either the real number field or the complex number field, so finite dimensional, that's just saying it's bounded and closed. Moreover, we can actually do something better. The spectrum is always contained in a disk with a large enough radius. Well, disk if you're on the complex plane, if F is the complex plane, or open interval if you're on the real line. And that radius cannot exceed the operator norm. Okay, so and that matches on to our first example. This was the right shift. There the operator norm is 1. And indeed, the whole spectrum was actually the closed unit disk, right? Which is disk of radius 1. So that matches nicely to that example, all right? So proof, well, it's a corollary of what we already know. So the proof of the last theorem revealed. So in the last theorem, what did I do up front? I expanded the resolvent into this power series, and that power series was convergent whenever lambda exceeds the operator norm in either absolute value or complex modulus. This part here, this first step, did not use that we are working over real or complex number field. That only kicked in later once we used complex analysis. Okay, so but in turn, this first step then shows that in particular all values lambda here are in the resolvent set. Right? Because for all those values, I can have a convergent power series representation for the resolvent, right? So that thing indeed exists, right? So the proof of the last theorem revealed that the set of all lambda that in either absolute value or complex modulus, depending on your field, is certainly contained in the resolvent, right? That's what we showed. Because you have convergent series representation for the resolvent operator. Okay, and so if you look at the complement, which is after all the spectrum, so F without rho of t, then set theory tells me that this has to sit in, well, a disk of radius, at most the operator norm. Okay, and that's already this statement which is up here. This here is this. Okay, good. But this subset of F, which is either R or C, well, is bounded. Well, because it sits in a disk of finite radius, so clearly that set is bounded. And since, remember, the resolvent is open, that means the complement is closed. And that complement is precisely the spectrum. All right. We obtain, that the spectrum, which is the complement of the resolvent, is both bounded and closed, hence compact. Okay. We obtain is compact. Okay, excellent. All right, so now we have some topological properties about the spectrum. We know it's compact. So whenever you do a problem and you end up with something non-compact there, then something went wrong. But I mean, these topological properties, they are, well, not really to the point. They don't say much. There's very wild compact sets, so that in this example that we did, everything was nicely symmetric, unit disk, but in general, this is absolutely not the case. Right? Anyways, we will build more theory now. So the next definition is about a curious object called, well, a spectral radius. So the last result established that the spectrum is always sitting in a disk of, sufficiently large radius. So now this next notion makes this more precise. So if you have a Banach space, T-bounded linear operator, and then we call, well, sort of the largest absolute value or complex modulus of the guy sitting in the spectrum, of all the guys in the spectrum. That's what we will call R of T. And this is the spectral radius. I have to write it on the next slide. The spectral radius of T. Okay, now here, since I don't require my Banach space to be always over the complex number field, that spectrum could be empty. So you take a supremum over an empty set, and that would be, of course, then minus infinity. Okay, so that's the convention. If that spectrum there is empty, then the least upper bound there would be minus infinity. All right, so that's consistent with the usual convention that you choose, hopefully, in real analysis. All right, so the supremum taken over the empty set equals, or is interpreted as minus infinity. Okay, fantastic. So now here comes the very famous theorem. It has its own name, spectral radius formula, which can be very useful if you're, usually when your operator has some symmetries built in. So self-adjoint ones, normal ones, unitary ones. There it's useful. For most other ones, it is more theoretical interest than useful in practical applications. So let X be again complex Banach space. We want to write down a general formula. So we want to make sure that our spectrum is non-empty. So that supremum there in that definition is not going to escape to minus infinity. Then we have the following curious relation. Spectral radius is, you take the operator norm of t to the power n. Well, there's clearly a mistake in my notes. Yep, there's a typo in my notes. I will correct it. You take the nth root of the operator norm of t to the n, and you send n to infinity. All right, this gives you the spectral radius. Moreover, special case, and those are the ones where you have some symmetry built in. If you're in a Hilbert space, complex Hilbert space there is, because you want non-empty spectrum, and you have a normal operator, is complex Hilbert space, and TLH normal, then the spectral radius is actually the operator norm. So all that n dependency up there in the first formula with the nth power and nth root, it goes out. And you just have this, all right? And that is certainly very nice, because in general, if you don't have the symmetry to estimate, I mean, how to say, to get a non-trivial estimate out of this formula is quite tough, right? Because, I mean, if you just use the ordinary submultiplicativity estimate, like this guy, then you will only find out that, well, the spectral radius is at most equal to the operator norm. And that's useless, because this you already know, because the spectrum is contained in a disk of that radius. So certainly the largest eigenvalue in complex modulus, the absolute value, cannot exceed that green quantity there, right? So to get a excuse me, to get a non-trivial information out of the spectral radius formula, if there's no symmetry for the operators present, is quite tough. Okay, good. So we'll prove this guy. It's quite a long proof, and again, this will be the second time that we will have to use complex analysis at some point. So, but early on, it starts harmless. So if lambda is in the spectrum, since so let's do here some algebra. So ordinary geometric sum tells me that I can write this in two ways. One is k0 n minus 1 lambda n minus 1 minus k t to the k, and in the other way you pull the lambda I minus t out to the right. So you have same structure, lambda minus 1 minus k t to the k, and then lambda I minus t. Okay, and here again we take t to the 0 as just the identity. And this is just, well, the geometric sum, the ordinary geometric sum, where you factor out 1 power. Okay, good. So now you have this. This is pure algebra, right? But since I start with something in the spectrum, this will be the last thing I write, and I will explain why this is so in the next video. If you're in the spectrum, then by definition either your operator is not injective or it is not surjective, right? So either that kernel here is non-trivial or the range is not everything, right? Since you are in the spectrum. And now I claim this implies immediately that the nth power of lambda has to be in the spectrum of the nth power of t. Okay, that's what I claim. I will stop now. I will explain this in the next video, and then we will complete the proof. This will take some time, and then we will assemble more theory. I will see you soon.